Module 4, Lecture B, Text File Workflows. By the end of this lecture, you will be able to read simple text-based engineering data files using built-in Python file handling, parse lines of numeric data for calculations such as station volumes or test averages, and write formatted results to output files for project records. Reading text files. Opening text files. To use external engineering data in Python, you first open the text file that contains the measurements or readings. Opening the file creates a connection that tells Python which file to use and that its contents will be read as input. Python can then read the text and bring the data into memory for further work. When opening a text file in Python, Python must know where the file is located. If it is in the same folder as the script, the file name is usually enough. Otherwise, you need to provide its full location. In engineering projects, clear file organization, consistent names, and predictable locations help prevent errors and make code easier to share and reuse. When reading a text file in Python, manage the resource carefully by making sure it is closed after use, often through modern automatic handling. This is especially important when working with many files, such as data from test specimens or weather stations. Also check the character encoding, since specialized data sources may require extra care. Opening a file is the first step in turning raw text into useful engineering data. Python code. Opening text files. This section focuses on working with engineering text files safely and carefully. You will create and open files using reliable handling practices, then read small rainfall records accurately. The code imports the path class from Python's pathlib module to work with file system paths more easily. This helps the program create, read, and manage paths in a way that works consistently across different operating systems. We use the path class from Python's pathlib module to create a reliable path to the rainfall data file. This approach makes file handling more consistent and works well across different operating systems. A small text string is created to represent engineering rainfall data, including headers and 2 sample records. The pathlib write text method then saves this content to the chosen file using UTF-8 encoding. This creates a simple text file that can be used for later processing. The file is opened in read mode using UTF-8 encoding, and a with statement ensures it closes automatically afterward. All lines are then read into a list so they can be processed one at a time later. The code counts the rainfall records by checking how many lines were read from the file, then subtracting 1 for the header row. This leaves only the actual data entries in the count. The code selects the first actual data record from the file contents by using the second line, since the first line is usually a header. It then removes extra white space from the start and end, so the line is clean and ready for later use. After reading the file, we confirm the results by displaying the opened file name, the number of data records read, and the first clean data line. We also check that the file was automatically closed, which confirms proper resource management. This script shows how to use Python's pathlib to read a text file safely. It creates a small rainfall data file, reads it line by line, counts the data records while skipping the header, and reports the first rainfall record. It also confirms that the file is closed automatically after reading, supporting proper resource management. Line by line. Reading a text file line by line lets Python handle sequential engineering records in order, such as measurements or readings. This makes it easier to inspect and clean data gradually, without loading the entire file into memory. It is especially useful for large logs or continuous data streams. Text files store data line by line, and engineering files may place values, labels, or mixed information on each line. When Python reads these lines, it treats them as text, so any values needed for calculations must be converted to numbers. Reading the file in order keeps the data organized and ready for analysis. Reading a file line by line makes it easier to handle small inconsistencies such as titles, blank lines, comments, extra spaces, or different line endings. It lets a program skip irrelevant text, detect unexpected content, and keep the process traceable. In engineering work, this supports clearer, more reliable file reading and better quality control. Python code, line by line. Engineering records can be read one line at a time, with each line first treated as text. Small files are useful for simple examples because they make the process easier to understand. A list is created to hold the lines of a sample survey text file. It begins with a header for station and elevation in meters, followed by data lines where each station value is paired with an elevation value. These lines will later be written to a text file for processing. The code adds a few more survey data lines for a sample text file. It includes station and elevation values at 50 meters and 75 meters, with a blank line between them as a separator. Together, these entries form a small demonstration dataset. The file Survey Profile Text is opened in write mode with UTF-8 encoding so it can receive data safely. The writeLines method then writes each string from survey lines in order. When the operation finishes, the with statement closes the file automatically, saving the data and freeing resources. The process begins by creating an empty list to hold processed records. The survey profile text file is then opened for reading with UTF-8 encoding, and each line is processed one at a time. Using the enumerate function also tracks each line's position in the file, starting from 1. The code cleans each line by removing extra spaces and new line characters before processing it. If the cleaned line is empty, it skips that line and moves on. This prevents blank or irrelevant lines from affecting the data processing. The code skips the first line of the file because it contains the header, not actual data. By moving directly to the next loop iteration, it ensures only data lines are processed and turned into records. The code splits each cleaned line into separate parts using spaces. It only continues processing when the line produces exactly 2 parts. Otherwise, it skips that line. This filters out any lines that do not match the expected format. The code turns each valid text line into a structured data point. It converts the station position and elevation values into floating point numbers, then stores them together as a pair in the records list for later analysis. The output gives a quick check that line-by-line reading worked correctly. It reports how many records were read, then shows the first and last records to summarize the range of data loaded. To find the overall elevation change, take the elevation from the first record and compare it with the elevation from the last record. Subtracting the starting value from the ending value gives the total change across the survey data, showing whether the elevation increased or decreased overall. The code reports the result of the calculation by printing the elevation change to 2 decimal places, showing the difference between the first and last records. It also confirms that each accepted data line was successfully parsed and stored as a record. This script demonstrates basic file handling and data processing in Python using simple survey data. It writes station and elevation values to a text file, then reads the file while ignoring the header and blank lines. Each valid line is converted into numeric values and stored as a record in a list. The script reports how many records were read, shows the first and last records, and calculates the elevation change between them. File reading basics. Reading a text file in Python brings a stored sequence of characters into your program, so it can be cleaned and used later. This matters in engineering work, because files such as notes or lab exports begin as plain text with no built-in meaning. Reading files safely is a foundation for reliable analysis, since errors at this stage can undermine even well-designed calculations. When working with files in Python, you should open them, read the needed contents, and close them to avoid resource problems. File data can be loaded all at once or read line by line, depending on the file size and task. Reading line by line is especially useful for large files because it avoids using too much memory. When reading files in Python, first confirm that the file name, path, extension, and read mode are correct so you do not fail to open the file or overwrite data. Be aware of text encoding and hidden characters, especially in files from different sources. After reading, inspect the raw lines for spaces, headers, or comments, treating the file contents as evidence before processing. This careful check helps ensure reliable data handling. Python code, file reading basics. This lesson shows how to create a small engineering text file, inspect its contents, and read it safely using built-in tools. It also explains how raw text can be converted into usable lines for further work. First, the project defines the data file location for the concrete strengths text file. Setting this path early makes it easy for the rest of the script to consistently find the file when reading from or writing to it. This defines a small, comma-separated dataset like one exported from a lab experiment. The first line gives the column names for specimen and strength in PSI, and the following lines pair each specimen identifier with its strength measurement. This simple CSV-style data will be used to demonstrate file reading. For this demonstration, the sample text is saved by opening the target file in write mode with UTF-8 encoding. This creates the file if needed, or clears any existing content, then writes the prepared data so it can be read later. Open the file in read mode with UTF-8 encoding so its text can be accessed safely. Then read the full contents into one string, which is useful when you need to inspect or process the entire file at once instead of reading it line by line. The code shows a quick preview of the file's raw text. It first announces the preview, then uses the representation function to display the first 60 characters, making hidden formatting or special characters easier to see. The file is opened in read mode with UTF-8 encoding, so text characters are handled correctly. Its contents are then read into a list of lines, making it easier to process each line individually later. Print the total number of lines to quickly confirm how many entries the file contains, including the header. Then show the cleaned header line to check the data structure, followed by the cleaned first data line to inspect the first actual values. Together, these checks give a quick overview of the file's contents. Each line from the file is cleaned by removing extra whitespace at the beginning and end, including new line characters. This creates a new list of trimmed lines, making the text easier to use in later processing. The code displays cleaned file records by removing new line characters from each line. This puts the data into a consistent, easier to process format for later analysis or transformation. This script introduces basic Python file handling using a small concrete strength dataset. It writes sample lab report data to a text file, reads the file back, previews part of the raw text, and inspects key lines such as the header and first record. It then cleans each line by removing trailing new line characters, turning the raw file contents into records that are easier to use for later analysis. Parsing numeric data. Parsing station data. Parsing station data means turning text file lines into usable numbers for engineering calculations. In civil and environmental work, each line often represents a station, with values such as distance and elevation. But a program first reads those values as strings. Before making estimates or summaries, the data must be identified, cleaned, and converted into numeric fields. Station data usually follows a recognizable pattern, but small formatting differences can affect how it is read. A line may include a station identifier followed by measurements, with spacing that varies by source. Effective parsing means understanding the line structure, extracting the needed values, and handling station identifiers consistently, so each measurement is mapped to the correct location. When reading station data, validate the file instead of assuming every line is correct. Real data can include missing values, extra spaces, or unexpected units, so parsing must convert text carefully and check that values and sequences make sense. Treating station data as structured information helps prevent errors that could distort estimates, quality checks, and engineering documentation. Python code, parsing station data. The key tasks are to read station lines from text, convert any numeric fields with care, and use the parsed values to make a simple estimate of earthwork volumes. A multi-line text block is set up to store station data for later earthwork volume calculations. It includes a header and several station records, each with a label plus cut and fill areas in square feet. Because the values are separated by spaces, the data is easy to parse and process. The station data is saved to a text file named station_earthwork.txt. The file is opened for writing with UTF-8 encoding, and a context manager ensures it closes automatically afterward. The station text is then written to the file so it can be stored safely for later processing. The process begins by preparing an empty collection to hold parsed station data. The station earthwork text file is then opened using UTF-8 encoding, and its first line is read as the header. That header is cleaned and split into column names, giving the program the structure needed to interpret the rest of the file. The code skips the header and processes each remaining line in the file. It removes extra white space, then splits the line by spaces to extract the station label, cut area, and fill area. This prepares the data for accurate parsing and later processing. The code verifies that each station data line has the three required parts: the station label, cut area, and fill area. If a line is incomplete, it reports the line number, skips that row, and continues with the next one. This prevents invalid records from being processed. The code converts a station label into a numeric distance for later calculations. It separates the label at the plus sign, takes the major station number, converts it to an integer, and treats it as hundreds of feet. Multiplying by 100 gives the station position in feet. The code changes the cut and fill area values from text into decimal numbers, so they can be used in calculations. It then stores each station's label, position in feet, and converted area values together in the records list. This keeps the data organized for later processing and analysis. The code first confirms that the station list contains at least 2 records, since volume calculations require 2 points. If there are fewer, it raises an error to stop the program before any invalid calculation can occur. The process begins by setting the total cut and fill volumes to 0, so they can be accumulated as calculations proceed. It then moves through each pair of consecutive station records, finds the distance between them from their station values, and uses that distance to estimate the earthwork volume for the interval. The average end area method estimates earthwork volumes between stations by using the distance between them and the average of their end areas. Cut volume is based on the average cut areas, and fill volume is based on the average fill areas. This provides a simple approximation of earthwork quantities from station data. Convert the cut and fill volumes from cubic feet to cubic yards by dividing each total by 27, because 1 cubic yard contains 27 cubic feet. This gives the volumes in a standard unit commonly used for construction and earthwork projects. The results are saved to a text file named Station Volume Summary. The file is opened for writing with UTF-8 encoding. Then the calculated cut and fill volumes are recorded to 1 decimal place, with cubic yards as the unit. This creates a clear record of the earthwork volumes for later reporting or reference. The code reports a concise summary of the processing results. It shows how many station records were parsed, lists the detected column headers to confirm the input was read correctly, and prints the calculated cut and fill volumes in cubic yards to 1 decimal place. It then confirms that the detailed results were saved to the specified output file. This script estimates earthwork volumes from station data. It writes and reads station information, converts station labels and area values into usable numbers, and checks that enough valid entries are available. It then uses the average end area method to calculate cut and fill volumes, converts them to cubic yards, and saves a summary file while printing the parse station count, headers, and final volumes. Numeric line parsing. Numeric line parsing converts text from data files into numbers that programs can use for calculations. Engineering files may look numeric to a reader, but the values enter a program as characters, so they must be split, cleaned, and converted. This turns human-readable measurements, such as 25, into the numeric value 25. Numeric parsing means reading each line, trimming extra spaces, splitting it by its delimiter, and interpreting each part by its purpose. Labels or identifiers stay as text, while measured values are converted into numbers for calculations such as averaging, comparison, or volume work. This separation helps prevent errors, such as treating labels as measurements or trying to calculate with text. When parsing numeric data, expect messy files with extra spaces, missing values, comments, or incomplete records. Define the expected structure, then skip or flag lines that do not match instead of quietly using flawed data. Clear handling rules are essential for maintaining data quality and producing reliable calculations and decisions. Python code, numeric line parsing. This script reads station records, converts numeric text into values ready for calculations, and safely reports any invalid records. A small list of raw text lines is created to simulate station records from a file. Each record contains a station label, followed by 3 numeric measurements, such as distance and cut, or fill areas. This simple setup provides sample data that can be parsed and processed later in the script. The script processes raw station data lines, where each record has a station identifier and 3 measurements. One sample record includes a missing value, while another contains 3 valid numbers. During processing, the script extracts the numeric data, validates each entry, and marks records with missing or malformed measurements as skipped. Set up 2 lists to separate successfully parsed lines from lines that cannot be parsed. This keeps valid data apart from problem records, making errors easier to handle without stopping the program. Iterate through the raw lines while tracking both the line number and the line text. Use enumeration starting at 1, so the numbering matches typical file lines. For each line, remove leading and trailing whitespace to clean the text before further processing. The code separates each cleaned line into comma-based fields and trims extra spaces. It only processes records with exactly 4 fields. Any line with a different number is recorded as skipped, along with its line number. This keeps incorrectly formatted lines from being processed further. Inside the try block, the code reads the station identifier as text, then converts the station feet value, cut area, and fill area into floating point numbers. This prepares the measurement data for later calculations by ensuring the numeric fields are in a usable form. The code adds a record to the valid data only after the station ID and 3 numeric values are successfully parsed. If a numeric conversion fails, it catches the error and saves the line number with the original text in the skipped records. This keeps invalid lines available for review while ensuring only valid data is processed further. For each valid record, calculate the net area by subtracting the fill area from the cut area. Then find the average net area by adding those results together and dividing by the number of valid records. This average represents the typical net area across the valid entries. The program creates or overwrites a summary text file for the station parsing results. It writes a short header, then records how many entries were successfully parsed and how many were skipped because of errors. This produces a simple summary that can be reviewed later. The code adds a summary line to a report file showing the average net area. It formats the value to 2 decimal places and labels it in square feet, helping summarize the parsed station data clearly. This numeric line parsing example reports how many station records were valid and how many were skipped. It then prints the average net area, shown to 2 decimal places, based on the difference between cut and fill areas in the valid records. Finally, it confirms that a parse station summary text file was created with the key parsing results. This script reads station data, converts valid text fields into numbers, and skips records that are incomplete or contain invalid numeric values. It stores the valid records, tracks the skipped ones, and calculates the average net area by subtracting fill area from cut area for each valid entry. It then prints a concise summary and writes the valid count, skipped count, and average net area to a text file. Handling header lines. Engineering data files often include header text before the numeric data, such as project information, dates, units, or notes. These details help people understand the file, but programs that expect only numbers can misread them and produce errors. Accurate automated processing depends on separating descriptive text from numeric data, so calculations like volumes or flow rates are based on the correct values. Before parsing a file, understand how its content is organized. Some files have a predictable header, such as one line of column names, while others include variable notes or comments before the data. When the format is fixed, skip the known header lines. When it varies, check each line to identify where data begins. Careful header handling helps prevent conversion errors and incorrect calculations. Headers are an important part of a data file, not something to ignore. They preserve details like units and column names, which help confirm that files are being read correctly. This is especially important when working with similar files or when a lab changes the column order. Treating headers carefully helps prevent misinterpretation and supports accurate engineering results. Python code. Handling header lines. This example shows how to ignore descriptive file headers and begin reading numeric station data after the column labels. Once parsed, the values can be used for simple engineering calculations. Define a file name variable to store the name of the text file used for the engineering data. Keeping the file name in one place makes the code clearer and easier to update when reading from or writing to the file. A string variable is used to store sample engineering text that represents a small data file. It includes brief header information about the project and units, followed by column labels for station, cut area, and fill area. The remaining lines contain numeric station data, setting up the text for later parsing and engineering calculations. The script creates or overwrites a text file in write mode and uses a context manager so the file closes automatically. It writes sample engineering style data, including headers and numbers, using UTF-8 encoding to handle special characters. This prepares the file for later reading and processing. We organize the file data into two groups, one for header information such as metadata, project details, or units, and another for station measurement records. Keeping descriptive text separate from numeric station data makes the information easier to manage and prepares it for later calculations. The code reads a text file using UTF-8 encoding and processes it line by line. Each line is cleaned by removing extra whitespace at the beginning and end. This makes it easier to correctly identify whether the line contains a header or numeric data. The code trims each line and checks whether anything remains. If the line is blank, it skips it and continues with the next line, preventing empty lines from disrupting the data processing. The code separates each line into fields based on whitespace, then tries to convert those fields into decimal numbers. If the conversion fails, the line is treated as non-numeric header information and stored separately. This allows the code to identify header lines while keeping numeric data rows for processing. The code keeps only station rows that contain exactly 3 numeric values: station position, cut area, and fill area. Valid rows are added to the station records, while incomplete or non-numeric lines are ignored. This ensures later calculations use only complete, reliable data. The code verifies that there are at least 2 rows of numeric station data before continuing. If fewer than 2 records are available, it raises an error because there is not enough data to calculate meaningful differences or averages between stations. Begin with the total volume set to 0. Then move through each pair of neighboring station records. For each pair, find the distance between stations by comparing their positions. This distance is then ready to be combined with the average net area to estimate the volume between the stations. Find the net area at each station by subtracting the cut area from the fill area. Then average the 2 net areas by adding them and dividing by 2. This average is used to estimate the volume between the stations. The code estimates total volume using the average end area method. For each pair of stations, it multiplies the average net area by the distance between them to find the segment volume, then adds that value to the running total. This gives an overall estimate of net volume across all station intervals. The code prints a short summary of the processed file: how many header lines were skipped, how many numeric station rows were parsed, and the estimated net volume rounded to one decimal place. It also displays the first header line as a quick reference to the file's initial metadata or description. This script reads an engineering data file, separates header information from numeric station measurements, and verifies that there are at least 2 station rows. It then estimates net volume with the average end area method by comparing fill and cut areas between stations. The output summarizes the number of headers, the number of data rows, the estimated volume in cubic feet, and the first header line. Writing project reports. Output file basics. Output files let engineering programs turn temporary calculation results into permanent records that can be reviewed and shared later. After processing data such as measurements or test results, Python can save the results by opening a file, writing the information, and closing it to complete the save. This makes the analysis available beyond the original program session. When creating output files, choose the mode carefully. Writing mode creates a new file or replaces an existing one, which can erase data, while appending mode adds new content to the end and preserves what is already there. Using the write mode helps manage information responsibly, such as overwriting drafts but appending ongoing records, like rainfall totals. Treat an output file as a document that others may need to understand later. Even plain text should include enough structure, such as a title, date, clear labels, units, and separated results, so the information makes sense without rerunning the program. This makes the file useful for communication, decisions, and broader project documentation. Python code. Output file basics. Create a clear project output file by using write mode when starting a fresh report. After saving, confirm the result by reviewing a brief preview of the saved content. A list of station results stores each station's volume measurement as a pair of values. Each pair includes a station identifier and a volume in cubic yards, making the data easy to organize, loop through, and use for reporting later in the script. Choose a clear descriptive output file name, such as stationvolumereport.txt, so the project results are saved in a file that is easy to recognize and find later. The program opens the report file for writing, creating it if needed, or replacing its contents if it already exists. It uses UTF-8 encoding so text is handled correctly. The file is opened with a context manager, which automatically closes it afterward, helping prevent resource leaks even if an error occurs. The code adds the report title Station Volume Summary at the top of the file. This header clearly tells readers what the file contains before the data begins. The code adds a simple report header by writing the project name, training example, and the measurement units, cubic yards. These lines give readers the context they need to understand the volume data that follows. The loop goes through each station and its volume, preparing that data to be written to the output file. Its purpose is to format each station's entry clearly for the final report. This line builds a clear message for one station's volume measurement. It inserts the station identifier and formats the volume to one decimal place, followed by the unit cubic yards, so each station's output is consistent and easy to read. This line adds each station's formatted information to the output file. It records the station identifier and its volume in a clear, readable way, helping build the final report. To preview the report, open the file in read mode so you can access the content that was just written. Using UTF-8 encoding helps the file handle many types of characters correctly, making it ready to read, process, or display. The code loads the file as a list of lines, then keeps only the first 6. This creates a short preview of the report, giving users a quick look without showing too much information. The code prints a console message confirming that the output file was created successfully. It includes the saved report's file name, so the user knows where to find the generated output. The program first prints a message telling the user that a preview of the saved project report is about to appear. It then joins the preview lines into one text block and displays them, giving the user a quick way to check that the report content was written correctly without opening the file. This script creates a simple text report for station volume data and saves it to a file. The report includes basic header information such as the title, project name, and units, followed by formatted volume entries for each station. After saving, the script reads back a few lines as a preview and confirms that the file was created. This is a useful way to turn data into a clear, human-readable report. Formatted output files. Formatted output files turn raw calculation results into clear engineering records. Each value should include context, such as its meaning and units, so the results can be understood and checked. Good formatting with consistent labels and project details supports clarity, error checking, comparison, and use with other tools. This makes the report a reliable part of the project documentation. Format numerical results with only the precision that is justified, since extra decimal places can clutter reports and imply false accuracy. Choose suitable digits and units for values such as distances, volumes, percentages, and measurements based on professional expectations. Keep spacing and alignment consistent so reviewers can read and compare data easily. When creating formatted output files, design the format around how the file will be used. For human readers, use clear labels, spacing, units, and simple summaries, such as totals or averages. For programs, keep the structure consistent with predictable separators. Deliberate choices about titles, precision, and organization help prevent confusion and support a reliable workflow. Python code formatted output files. Format civil engineering reports with clear columns, practical units, and output files that are easy to read and trace. The code imports the path class from the pathlib module to work with file system paths in a reliable, cross-platform way. This makes it easier to create, manage, and access paths when reading from or writing to files, reducing errors caused by path handling. The script creates a records list to store small earthwork results. Each item represents one project station and includes the station label, the cut volume, and the fill volume, with volumes measured in cubic yards. Organizing the data this way makes it easy to access, update, and use later for reports or calculations. The code creates a pathlib path object to represent the project report file. This provides a simple cross-platform way to refer to the report location before writing the formatted output. To assess the earthwork balance, add all cut volumes to find the total material to remove, and add all fill volumes to find the material needed. Then subtract the total fill from the total cut. The result shows whether the project has excess material or a shortage. The report file is opened for writing with UTF-8 encoding, using a safe file context so it closes automatically when finished. The report begins with the title, Earthwork Summary Report, followed by the project name, Training Road Alignment. A neatly aligned table header is then added for station, cut, fill, and net earthwork values in cubic yards, creating a clear professional layout. The process goes through each earthwork record, calculates the net volume by subtracting fill from cut, and uses that result to show whether material was removed or added at each station. It then writes the station, cut, fill, and net volume to a report in neatly aligned columns, with numbers rounded to 1 decimal place for readability. The file output adds a blank line for readability, then records the key earthwork totals. It lists the total cut volume, total fill volume, and net project volume, each rounded to 1 decimal place and labeled in cubic yards. Together, these values summarize the material removed, added, and the overall balance of the project. The code reads a report file as UTF-8 text, splits it into lines, and prints a preview made from the first 8 lines. It labels the preview clearly, then prints the report's absolute file path, so the user knows exactly where it was saved. This script creates a clear text report for earthwork data in a civil engineering project. It summarizes station cut and fill volumes, calculates total cut, total fill, and the net difference, then saves the organized results in an earthwork report text file. It also previews the first few lines and prints the saved location, making the report easy to review and suitable for project documentation. Saving report files. Saving report files turns calculations into reliable project records that can be reviewed later. Use clear names, locations, and consistent formats so others can find and understand the results. When creating text output with Python, make sure the file fits into the project's documentation or quality control workflow as part of an organized evidence trail. When saving report files, choose whether to create a new report, update an existing one, or add new data based on the report's purpose. Separate reports can preserve distinct records, while ongoing files can support continued analysis. Protect final deliverables from accidental changes. Label them clearly, and keep working logs organized so updates remain traceable. When saving report files, make them portable and clear for others to use. Plain text is easy to share, but it needs enough context, such as a title, project ID, date, units, and a brief results summary. Clearly labeling units and material categories helps prevent confusion and supports accurate professional documentation. Python code. Saving report files. Save reports with clear project details. Use text files for records that remain easy to preserve, and keep outputs small enough to read and manage easily. The script begins by importing tools for working with file paths and dates. The path class helps manage file system paths in a clear, cross-platform way, while the date class lets the script include the current date in a report. The setup defines the project being reported on, records the current date to timestamp the report, and chooses a dedicated folder for saving the output. It also uses a path handling tool to manage the report directory in a clear and reliable way. The code prepares a report file location by first making sure the output folder exists, creating it if needed, without raising an error if it is already there. It then builds a report file name using the project identifier, the current date, and a descriptive suffix. Finally, it combines the folder and file name into the full report path using pathlib path joining. The data is organized as station numbers paired with their earthwork volumes, making each station's value easy to manage. The total volume is found by adding all station volumes together, and the average volume is found by dividing that total by the number of stations. This gives both the overall earthwork amount and a typical volume per station. The report file is opened in write mode with UTF-8 encoding, creating it or replacing any existing version. The file then begins with a clear title, followed by the project identifier and the creation date. This gives the earthwork quantity report a simple, organized header with the key context included. The code creates a report table for station volumes in cubic meters. It writes the unit label, adds column headings for station and volume, then loops through each station entry. Each line is formatted with aligned station numbers and volumes rounded to 1 decimal place before being written to the report file. The code writes a formatted report line for each station and its volume, aligning the values neatly and showing each volume to 1 decimal place. After all stations are processed, it adds a blank line and then writes the total volume, also rounded to 1 decimal place, to summarize the results. The code adds a summary line to the report showing the average station volume. It formats the value to 1 decimal place, making the report clear and easy to read. The code confirms that the report was saved successfully, then shows where the file is stored and what it is called so the user can find it easily. It also prints the calculated total earthwork volume, rounded to 1 decimal place and labeled in cubic meters, giving a quick summary of the report's main result. This script creates a dated text report for a project's earthwork volumes. It prepares a report folder, calculates total and average volume from station data, and records each station's volume along with the summary values. After saving the report, it confirms where the file was stored and shows the total volume in cubic meters, keeping the project data organized and easy to access. In this lecture, you learned to read simple text-based engineering data files using built-in Python file handling, parse lines of numeric data for calculations such as station volumes or test averages, and write formatted results to output files for project records. In the next module, Module 5, we will go over none. Thank you for your attention. See you all in the next lecture.